Quiz. So on today's quiz, we're asked to calculate mass percentages, mole percentages, and do conversions involving mass and mole percent. So let's address our first question, which is really a combination of a mass percentage question and a nomenclature question. So I'm asking you, what's the mass percent of nitrogen in ammonium nitride? And again, remember how I was emphasizing, you need to know your nomenclature. Ammonium nitride. Would someone like to volunteer a formula for ammonium nitride? Yes. Yep, NH4 3N. So ammonium is NH4 plus, and nitride. What does the IDE signify? Are we dealing with a polyatomic or a monoatomic ion? IDE, monoatomic. So it's N. Nitrogen's a 5A element. 5 minus 8 gives us -3. So that's why we have N3 minus. We cross our charges, and that gives us NH4 parentheses 3N. So that tells us that we have 3 nitrogens and how many hydrogens from the ammonia? What's 4 times 3? 12. So we have a total of 4 nitrogens and 12 hydrogens. So if we want to calculate mass percent, why is this so important? Why do we need this information? If I wanted to calculate the mass percent of nitrogen, what 2 pieces of information will I need? Molar mass, yep, and the mass of nitrogen. So we need the mass of nitrogen as well as our total mass. Okay, so let's go about calculating those 2 quantities. So the mass of nitrogen. So we have 4 nitrogen atoms, and what is the atomic mass of nitrogen? 14, yep. Okay, so then if we're calculating the mass of nitrogen, 4 times 14, punching that into our calculator, gives us a mass of 56 grams of nitrogen. We can repeat this calculation for our total mass. So our total mass is equal to the mass of nitrogen, which is 4 times 14, plus the mass of hydrogen. How many hydrogen atoms do we have? 12. So we have 12 times 1 to follow the same consistency. So adding 12 to our total gives us a total mass of 68 grams. Okay, perfect. So then all we have to do to calculate the mass percentage of nitrogen is we take the mass of nitrogen, which is 56 grams, over our total mass of 68 grams times 100%. And that in turn gives us a mass percentage equal to, let's now switch to our document camera. So we're going to take 56 divided by 68 times 100, and that in turn gives us a percentage of 82%. Does that make sense to everyone? Whoops. So what we're now going to do is we're going to assess the next question, which is also a nomenclature-derived question. Again, when I mentioned that you should focus on your nomenclature, I'm really not kidding when I say that. So we're asked, what mass of copper 3 sulfate contains 15.6 grams of sulfur? Would someone like to volunteer a formula for copper 3 sulfate? Jacqueline? C2SO4. Yes, exactly right. So let's summarize the logic behind that. So we have copper 3 plus, since it's copper 3. Sulfate has a charge of 2 minus, and crossing the charges gives you Cu2SO4 3. Does that make sense? Now that we have this information in hand, let's set up a solution map. So we're starting off with 15.6 grams of sulfur, and in the end, we want to report the grams of copper sulfate. To accomplish this, what units will we have to go through? What was that? That's right. Moles, right? Yeah. So let's be specific here. Moles of what and moles of what? So we're going from grams of sulfur to moles of sulfur. And then from moles of sulfur, we're going to go to moles of copper sulfate. Yep. This is a classic relationship between the moles of an element and the moles of a compound, obtained using our formula ratio. So then, let's now focus on executing on this. So if we have 15.6 grams of sulfur, and this is monoatomic sulfur, if we're going from grams to moles, what units need to be on top? Moles. So in 1 mole of sulfur, we have how many grams? 32. Yep. Perfect. And my question to all of you is, how many moles of copper 3 sulfate do we have per mole of sulfur? So in 1 mole of copper sulfate, copper 3 sulfate, how many moles of sulfur do we have? How many sulfur atoms do we see? 3. Yep, we have 3 moles of sulfur. Okay, and then finally, if we're going from moles to grams, what conversion factor do we use? Moles to grams, molar mass, exactly. So how many grams are present in 1 mole of copper sulfate, Cu2SO4 3? So what is the molar mass of copper 3 sulfate? Would someone like to volunteer a molar mass? We want to get in the habit of calculating molar masses quickly. What was the molar mass of this compound? Let's showcase as a sidebar calculation the molar mass calculation, but 415 sounds about right. So how many copper atoms do we have? 2. So then we have 2 copper atoms. And what is copper's molar mass about? 63, about 63.5. Okay, so as our sidebar calculation of the molar mass, we have the number of copper atoms times the mass of copper. How many sulfur atoms do we have? 3. And we know the mass of sulfur is 32 grams. What's the mass? How many oxygen atoms do we have? What's 4 or 12? 12. So we take our 12 oxygen atoms times 16 grams, and that in turn gives us a molar mass of, let's punch it in, 2 times 63.5 plus 3 times 32 plus 12 times 16 gives us a molar mass of 415 gram per mole. So we'll plug that in up here. We now have all the information we need to complete this problem. Does that sidebar calculation make sense? Okay. So let's now execute on this. So we're going to take 15.6 divided by 32 divided by 3 times 415. And you should get as a grand total about 67.4 grams. Does that match what you've observed on your calculator? And I would recommend following along on your calculator just to make sure you're inputting everything correctly. So then that in turn gives us a final mass of 67.4 grams of copper 3 sulfate. Does that make sense to everyone? Okay, so let's now continue on with our next and final problem. So this last problem is a mass percent conversion. So let's erase this distracting molar mass calculation. Let's just get rid of that for now. And we're asked in this next problem, how many moles of copper are present in a 15-gram sample of ore that is 40% oxygen by mass, with the remaining mass being copper. So this is a classic remaining mass percent problem. So then, We are given that we have 15 grams of ore. And in the end, we want to be able to report the moles of copper. Now, in order to get the moles of copper, what will we need to calculate? Yes, and the grams of what? Copper. Exactly right. Okay, now that we have this scheme in hand, let's think about what conversion factors we'll need. To go from the grams of ore to the grams of copper, we'll need what conversion factor? Yep, the mass percent, and let's be really clear here, we need the mass percent of what? Copper, exactly. Finally, to go from grams of copper to moles of copper, we would need what? So formula ratio allows us to go from moles of element to moles of a compound. But if we're going from grams to moles, what's that relationship? Molar mass or molecular weight? Exactly right. So let's now execute on this scheme and let's figure out how we can get the mass percent of copper. So we know if the remaining mass of our sample is copper and we know the mass percentage of oxygen, what must the remaining percentage be? 60, and that remaining percentage must be what? What is it? Oxygen or copper? Copper, exactly. So you can get the mass percentage of copper by taking 100% minus the mass percent of oxygen. Remember how we discussed these remaining mass problems last session? Okay, so we're going to take 100% minus 40%, and that in turn gives us a mass percentage of 60%. We are now ready to complete this problem. So if we have 15 grams of ore, my first question to all of you is, how many grams of copper do we have per how many grams of ore? What does our conversion factor look like? Grams of copper per gram of ore. How many grams of copper do we have per how many grams of ore? How can we write this percentage as a conversion factor of this form? 60 grams of copper per how many grams of ore? 100. Okay, perfect, perfect. Now, if we want to go from grams of copper to moles of copper, what units are going to be on top? Moles. So in 1 mole of copper, we have how many grams of copper? Yep, or 63.5. Okay, we now have all the information we need to execute on this setup. 15 times 60 over 100 divided by 63.5 gives us 0.14 moles of copper. Does that make sense? Yes. Yes, of course, for sure. So then, let's take 15 grams of ore times 60 divided by 100, then divided by 63.5. Does it match? Perfect. It's always good to check that everything's being entered correctly into the calculator. So again, keep brushing up on your nomenclature. You'll need it throughout this class, especially for the next few chapters we're discussing. Do we have any other questions on this quiz? If not, we're going to move on to our major lecture topic for today. Okay, so what we're going to talk about today is this idea of the empirical and molecular formula. So the empirical and molecular formula. So to set the stage and to give you a sense of why do we care about this, why are we talking about the empirical formula, many of the analytical methods, such as the data collected in laboratory experiments, will provide us the mass or mole ratio of elements in a sample, or they'll give us the mole percent or mass percent. Very rarely can an analytical method tell us exactly how many atoms are found in a given molecule. They can only tell us the ratio of atoms. Now, these ratios, these mass and mole ratios, give us what's known as the empirical formula. And we've seen this before in the law of multiple proportions, right? The empirical formula, quite simply, is the simplest formula that contains the smallest whole number ratio of elements that make up a compound. Now, you may say, why is that so important? The empirical formula can be thought of, and this is the way that I want you to think about it. It's the smallest whole number mole ratio of each element. It is fundamentally a mole ratio. Now, unfortunately, the empirical formula is not the full formula of our molecule. So often a separate experiment is done to get the molecular weight and allow us to determine the molecular formula. So the key thing I want you to star here is that the key to getting our molecular formula involves the molecular weight or molar mass. So the molecular formula, quite simply, is the number of atoms of each element in a compound. It's just the exact number. So let's look at an example of a molecular formula. For example, C6H6 is the formula for benzene. So this is our molecular formula. If we wanted to look at the simplest ratio of elements in this compound, how many moles of carbon do we have in this compound? Theoretically, 6. So we'd expect we'd have 6 moles of carbon per how many moles of hydrogen? 6. Now, 6 to 6 can be simplified, and in turn, we have 1 mole of carbon per 1 mole of hydrogen. In other words, CH would be considered our empirical formula. The simplest ratio of moles, or the simplest ratio of atoms of each element in our compound. Does that make sense? Okay. Now, let's talk a little bit on the nitty-gritty of how is the molecular formula calculated. Well, the way that we convert between the empirical and molecular formula involves calculating N. So the empirical formula is repeated N times, where N is the number of empirical formula units. This is not to be concerned. This is not to be confused with like ionic formula units. This is just telling me the number. Every time I write the formula of my empirical compound, for example, CH, this N tells me how many of these CHs I have. So for example, if N was equal to 2, how many CH units would I have? 2, exactly. So I draw 2 of them and it would be C2H2. So N tells me how many of these units, these empirical formula units, are found in my molecule. Now, the way that we calculate N is by taking our molar mass. So this is MW is our molar mass or molecular weight. And then we are dividing by the empirical formula unit mass, which I'd like to think of as the molar mass of the empirical formula. Does that make sense to everyone so far? So let's now look at an example. Let's look at an example. So I'm going to give you, we know, for example, we know that our empirical formula is CH2. Okay, let's suppose we know that our empirical formula is CH2. We run an experiment. We run a very carefully designed experiment to calculate our molecular mass or our molar mass. And we end up with a molar mass of 56. So we end up with a molar mass of 56. So then, let's show how we would calculate N. So our first order of business in this problem is given the empirical formula. Can I calculate a molar mass just like I've done whenever I'm given any other formula? Yes. So then our molar mass is equal to 12 for carbon times 1 carbon atom plus 1 for hydrogen times 2 hydrogen atoms. And that in turn gives us a molar mass of 14 grams per mole. Okay, we know that our molecular formula mass is 56 grams per mole. So do we have enough information to calculate N? Yes. So then, for N, we know that, oops, one moment. We know that N is equal to our molecular mass, which is 56 grams per mole, divided by our empirical mass. And allow me to calculate that, which is 14 grams per mole. This in turn gives us a value of N, if we punch it into our calculator, of 4. So what does that mean? What does that mean? How many of these CH2 units do we have? 4. Okay, so with that established, what we're going to do is we're going to use this idea. So we have our formula of CH2. So how many of these CH2s should I draw? 4. Okay? Now, if I count up my total number of carbon atoms, how many do I have? Oh, that was for hydrogen. So we have 8 hydrogens, yes, and how many carbons? 4. So it's C4H8. And I'm going to write this in purple because this is our molecular formula. So our molecular formula is equal to C4H8. Does everyone get the process behind figuring out N, writing out the number of formula units, and then counting all of your atoms to give you your molecular formula? To make sure we're all on the same page with that, I'm going to let you loose on the following example. The empirical formula of hydrazine is NH2, and its molecular mass is 32. And I want you to tell me the molecular formula of hydrazine. Everything going okay? Everything going okay? Do you have any questions? Everything going okay? Everything going okay? Yes. Yeah, and remember it's NH2. Yeah. Yeah. Everything going okay? Yep, exactly right. Oh, yep, that looks good. Yep, looks good. And then you just add your atoms together. Yep, looks perfect. Yep, looks good. So let's come together to discuss this problem. I saw a lot of reasonable solutions. So let's just color code what information we have. So we know our empirical formula. Our empirical formula is NH2. My next question, can we calculate the mass of this empirical unit? Yes. So then we can figure out that our molar mass is 14 for nitrogen plus 1 times 2 for hydrogen, which in turn gives us a molar mass of 16 gram per mole. Perfect. We also are given, whoops, one moment. We also are given that our molecular mass is 32.0 gram per mole. So do we have enough information to calculate N? Yep. So N is equal to our molecular mass, which is 32.0 gram per mole, divided by our empirical mass, which is 16.0 gram per mole. And just looking, if you punch this into your calculator, this gives us an N value of 2. So then, from that, if we want to write out our molecular formula, how many of these empirical units am I going to write? 2. So I'm going to write this as NH2, NH2, which translates to how many total nitrogens? 2. And how many total hydrogens? 4. So this is N2H4. Hydrazine, also known as the principal component of rocket fuel in terms of starting off that whole process. Any questions on this example? Okay, let's keep going then. So one thing that I really want to establish is that molecules can have the same empirical formula with a different molecular formula. So let's compare, for example, N2O4 and NO2. So as we're switching to determining empirical formulas, let's now switch pen colors and let's look at the ratio of atoms of each element. So in N2O4, we have how many theoretical moles of oxygen? Yep. So we have 4 moles of oxygen per how many moles of nitrogen? How many moles of nitrogen do we see? 2. So 4:2 ratio. That can be simplified, right? 4:2 can be simplified to 2:1. So we have 2 moles of oxygen per 1 mole of nitrogen. So that would give us an empirical formula of NO2. Now, if we do the exact same analysis for NO2, is there any simpler ratio of elements? Is there any smaller whole number ratio that I could write? No. So then we see NO2 also has an empirical formula of NO2. These are different compounds, different chemical species, but do they have the same empirical formula? Yes. So how do we tell these two compounds apart? What's our trick? How do we tell these two compounds apart? What's different about them? Molecular weight. Exactly right. Exactly right. So to distinguish two species with the same empirical formula, we know that these two species will have different molecular weights. And that's our key to get us out of this conundrum. So that's why often 2 experiments need to be done to definitively assign the formula of a compound. Everyone okay so far? Okay, we're now going to get into this point where we're going to be able to do a little bit of math and talk a little bit about some tricks to calculate the empirical formula efficiently. I'm a really, yes.
Actually, going back to the example.
Yes.
Where we calculated for hydrazine.
Yes.
Would we simplify that, or would we just leave it as is?
You leave it as is because the molecular formula describes the exact number of each element found in your compound. The only time when you simplify is if you're writing the empirical formula. Okay, so in this next section, we're going to be using our equations for mass percent and mole percent And our goal is to use algebra to find a general way to calculate the empirical formula. I'm a big believer in using algebra and using math to solve problems in chemistry. It makes your life easier. Instead of doing a problem 50 times in 50 different ways, you can write one solution and just use the same equation to solve these types of problems. So, but in order for you to effectively use this equation that I'm going to talk about, we're going to need to go through the steps on how I obtain this equation. So let's establish at the start of this exercise, what is our goal? What is the empirical formula in the simplest words? What did I describe it as? A ratio of what? The empirical formula is a ratio of what? I heard it in the back. It was the simplest ratio of the moles of each element. It is a mole ratio. So when we think about our empirical formula, we're really thinking about the moles of element 2 over the moles of element 1. And I'm going to write the moles as N. So our empirical formula can be thought of as N2 over N1, where N2 is equal to element number 2, or the moles of element number 2, and N1, which I'm going to change colors and use a slightly different pen color to make things easier. N1 is the moles of element 1. Okay, so now that we have our color-coded scheme, let's think about where we can write out this mole ratio. How can we get this mole ratio? Okay, so one assumption that I'm going to show you right now is that the moles of element 2 over the total moles times 100% is equal to the mole percent of element 2, where mole percent 2 is the mole percentage of element 2, right? Now, another way that we can write this is the moles of element 2 are equal to the mole percent of element 2 times the total moles over 100%, right? We have used this exact mole percentage equation before. Now, we can do the exact same thing. We can repeat the exact same process for element number 1. So the moles of element 1 are equal to the mole percentage of element 1 times the total moles over 100%, right? Exact same equation, except we're using the mole percentage of 1 this time. Okay. So from this, if we plug in each of these moles into this top empirical formula equation, we're going to see something a little bit interesting that we can use. So we know now that N2 over N1, so N2 over N1, which is our mole ratio, is equal to, and this is where you're going to see a lot of terms cancel out, the mole percentage of 2 times N total over 100% divided by the mole percentage of 1 times N total, the total moles over 100%. Now, the whole reason why I've taken us through this song and dance is because we see, are these N total over 100 terms the same? Yes. So then they cancel out. So we can think of our mole ratio the same way we can think of as a ratio of mole percentages. And that is far more useful in our calculations than just looking at a normal, than looking at the absolute number of moles. Okay, so here's what we've established so far. The ratio of moles is the same as the ratio of mole percentages, right? Okay. Now let's move on to our next idea. So how do we calculate moles? If I wanted to calculate the moles of an element, what would I need? How do I calculate moles given mass, for example? Molar mass, exactly. So the moles of element 2 would be equal to the mass of element 2 over the molar mass of element 2, right? We can get mass, we can get moles from mass really easily, right? Okay. Now let's think, how do we calculate mass from mass percent? And just like our equation for mole percent, we can calculate the mass of an element by taking the mass total of our mixture times the mass percent of element 2 over 100. This equation is found in your notes when we discussed how we calculate the mass of an element given mass percent. Does this form look familiar? Does this conversion factor look familiar that we've been using throughout our mass percent calculations? The mass percent over 100 grams per 100 grams. So we've seen this before. Now, let's now combine and let's write out another equation for the moles of element 1. And will the moles of element 1 equation look almost exactly identical? So N1, so when we think about the moles of element 1, is it calculated in the exact same way? Yes, the only thing that's changing is instead of a 2 label, instead of using the mass and molar mass of element 2, we're going to use the mass and molar mass of element 1, exactly. So then, the mass of element 1 is obtained in the exact same way from the total mass. We take M total times the mass percentage of element 1 over 100%. And you may be thinking at this point, why are we going through all this effort? This seems like a lot of work for something that doesn't have a lot of value. Well, we're working towards this idea. We've established already we want our mole ratio, right? We want our mole ratio. So what we're going to do is we're going to take N2 over N1, and we're going to plug in and substitute into each of these equations. So in the end, so I'm going to write it out from start to finish. So let me switch pen colors. Give me one moment. So N2 is equal to M2 over molar mass 2. Let me set it up so we can see both of that. Here we go. Now, what did we say just moments ago that mass 2 was equal to? Can we substitute for mass 2? Yes. So let's plug in that whole expression. So we have the mass percentage of 2 over the molar mass of 2 times the total mass, M total, over 100%. And I'm suggestively leaving this M total over 100% term off to the side. Everyone following so far? We've just plugged in this expression for mass 2 into this equation. Now we can do the exact same thing for the moles of element 1. And we know that N1 is equal to M1 over molecular weight 1. Now, will this equation for the moles of element 1 look exactly identical to the equation for the moles of element 2? Yes, except we're just going to change our labels from 2 to 1. That's it. So then the mass percent of element 1 over the molar mass of element 1 times M total over 100%. Okay. Now, when we've established, and we've established thoroughly now, that we want a ratio of moles, right? We want a mole ratio. Do we have an equation for each of the moles? Yes. So now we just have to take the ratio. Okay, so N2, so we have the mass percentage of 2 over the molar mass of 2 times M total over 100%. And we're dividing N2. We're dividing N2 by N1. And we know that N1 is the mass percentage of 1 over the molar mass of 1 times M total over 100%. And does the total mass cancel? Does the total mass actually matter at all when you're calculating the empirical formula? No, not at all. So it cancels out. And we're left with, and this is the equation that you're going to want to use, is that the empirical formula, or the simplest mole ratio, is equal to N2, which is the mass percentage of 2 over the molar mass of 2 divided by N1. So times the molar mass of 1 over the mass percentage of 1. And in the end, we have developed, and let me zoom in on this equation and put a box around it. We have developed an equation to calculate the mole ratio and to calculate the empirical formula given what two pieces of information? What do we need? Yep, mass percents. And what else do we need? Molar mass. Or in this case, the mass of your element. Yeah. So let's put this equation into practice. Let's put this equation into practice. I can't necessarily just say this is useful. Let's prove that it's useful. So let's apply this equation to an example. But for those of you that want to do and calculate the empirical formula the longhand way, let's talk about how you do that the longhand way. So let's compare. You're welcome to use either method, but let me show you how you would do it the longhand way. So if you're given the mass percent of each element, you can obtain the empirical formula in a step-by-step process. So step 1, you'd convert the mass percent to mass. And in this case, you're allowed to assume a total mass of 100 grams. And we've established already that the total mass doesn't actually matter, right? It cancels out. So you can assume whatever total mass makes the math easier. So we know that, for example, the mass of your element is, the mass of your element is equal to the mass percent over 100 times the mass total. In this case, the mass total is 100 grams. So the convenient point about assuming a total mass of 100 grams is that you can just read off the mass percentages as the mass. That's why you assume 100 grams if you're doing it the longhand way. Next, if you're doing this step by step, you'd want to convert mass to moles. So then, if I wanted to calculate the moles, how do I calculate moles for mass? I take the mass and I divide it by what? Molar mass, exactly. Moles are the mass divided by the molar mass. So you can convert mass to moles. No problem at all. Now, once we have our moles, what we're next going to focus on is how do we actually go from the moles of each element and the mole ratios to a valid empirical formula. And to help us along with that, I like to just go on this idea where you're going to choose an element. So you're going to pick an element. So for example, let's suppose we have 2 different elements at play and we've calculated the moles for each. So you have your mole values, they're present on your piece of paper, and your goal now is to just pick an element. You pick whatever one you want, doesn't matter. and you're going to divide the moles of every element by the moles of the chosen element. And this is a lot of words for something that in practice is very simple. So let's suppose we're given that our moles of oxygen are 2, our moles of carbon are 1.5, and our moles of hydrogen are 2. So which moles do you want to pick to divide everything by? In general, I like to pick the smallest number of moles. Oxygen, carbon, or hydrogen? Which one would you want us to pick? What was that? Carbon. Sure. Let's pick carbon. So let's take the moles of oxygen over the moles of carbon. So we have 2 moles of oxygen over 1.5 moles of carbon. And that in turn gives us 1.33 moles of oxygen for every 1 mole of carbon. We're going to repeat this process for each element in our compound. We're going to repeat this process for each element in our compound. So the moles of carbon per the moles of carbon, this one's a bit of a, it's a bit of a freebie. If you divide the moles of something by the moles of that same thing, are these the same quantity? Moles of carbon over moles of carbon? Yeah, so it's inherently going to be 1-to-1. So we have 1 mole of carbon per 1 mole of carbon. Let's now fill in. Oops, one moment. Let's now fill in the mole to mole ratio for hydrogen. So let's take the moles of hydrogen per mole of carbon. So we have 2 moles of hydrogen per 1.5 moles of carbon. And that in turn gives us 1.33 moles of hydrogen per 1 mole of carbon. Okay, so we've calculated all of our mole to mole ratios. So if you use that equation that we derived previously, the equation that we talked about earlier will give you the mole to mole ratios. So now we're at the same point from both of these processes. We've gotten the mole to mole ratio. However, we're not quite done, because looking at our mole to mole ratios, do we have the simplest whole number ratio? Are these whole numbers? Do we see decimals here? Yes. So then we have to convert these decimal mole ratios to whole numbers. And to do that, what we're going to do is you're going to multiply all of your mole ratios by the same whole number. By the same whole number to give you the smallest whole number mole ratio. Okay, so let's rewrite what we have from before. So we know that we have 1.33 moles of oxygen for every 1 mole of carbon. We also know that we have 1.33 moles of hydrogen in 1 mole of carbon. Now, when I see 1.33, I'm going to try to think of a fraction that matches 1.33. And 1.33 to me matches exactly the fraction of 4/3. Don't worry, I have a cheat sheet on the bottom of this page to help you correlate decimals with fractions. If you're ever unsure and you want to try out what you can do using your calculator is you can try out different fractions. So you can punch in 4/3 and you'll see it perfectly matches 1.33. Is everyone seeing that in their calculator? Okay. Now, if we want to convert 4/3 into a whole number, if we want to get rid of this bottom denominator, if we want to get rid of this 3 on the bottom, what do I need to multiply all of these ratios by? 3, exactly. So 4/3 times 3 is equal to 4. And it's this 3, this same whole number, that you're going to multiply all of your mole ratios by. So if we have moles of carbon on the bottom, we're going to multiply by 3 of what to get rid of this moles of carbon? We're going to have how many? We're going to multiply by 3 of what? Moles of carbon, exactly. So we're going to multiply by 3 moles of carbon. Okay? So that in turn gives us 4 moles of oxygen, 4 moles of hydrogen, and this is really important, how many moles of carbon do we have? 3, because that's what we chose for our whole number. So then, if we had to write our empirical formula, how many carbons would I write? 3. How many hydrogens would I write? 4. And how many oxygens would I write? 4. There we go. Does that process make sense? You write your mole ratios, you take a look at your decimal. You convert your decimal into a fraction. And then you find a whole number, in this case 3, that you multiply all of your mole ratios by to give you whole numbers. Yes. So 1.33 matches the fraction of 4/3. So if we want to convert this fraction into a number, we need to multiply by the denominator. Exactly. And to help everyone recognize the common fractions, I have a trick for you. So this is a table of common fractions and the whole number you should multiply by. So I want you to box in purple or box in whatever color you can, these whole number cheat sheets. So essentially, let's talk about how we can use this table. So for example, if you see 0.33 as your decimal, that corresponds to a fraction of what? 1/3. So what should we multiply by? 3. If we see a fraction of 0.5, that corresponds to 1/2, and we should multiply by 2. Okay. So you can even do this with your calculator. One trick that I like to do, so if I'm looking at my decimal and I'm just stuck and I don't remember my table, I'm just going to try multiplying by whole numbers. So I'm going to try multiplying by 2. Does that work? Do I see decimals still? Yeah. So that's a dead end. So I'm going to divide by 2. I'm going to multiply by 3, and lo and behold, I get a nice, clean whole number. So you can literally just try multiplying by whole numbers until you get a whole number out. So don't ever feel like you're stuck on the exam just because you forgot the table, okay? You have the tools available. Everything going okay so far? Yes. Oh, then you'd have to just try using the brute force method. You just have to try with different whole numbers. Yeah. But most compounds don't have like very odd ratios. Typically the ratios are relatively consistent. Yeah. Okay. Now we've already done this next example. We've written out the whole number mole ratio of each element into the subscript for that element in the empirical formula. So we said we have C3H4O4. Now this mole ratio, this whole number mole ratio represents what formula? Empirical. So in effect, we've done in each of these steps is we've calculated the empirical formula. Now, step 7 is optional. It depends on the problem. If you are given the molecular weight, you're going to want to calculate N. So for example, Let's suppose we are given that our molar mass is equal to 208. If we know our molar mass and we know our empirical formula, do we have enough information given to calculate the molecular formula, to calculate N? Yes. Have we done that earlier on in this class? Yeah, we have. So then let's walk through how we would go about doing that. Let's walk through how we would complete this. So if we know our empirical formula is C3H4O4, let's figure out the molar mass of this empirical unit. So take a moment, punch it into your calculators, and then we'll discuss in a few seconds. Try to calculate the molar mass of this empirical subunit. And when anyone wants to volunteer, don't be shy to raise your hand. What was that? 104, exactly right. So the molar mass is 104 gram per mole. So then we can calculate N. So N is equal to 208 gram per mole over 104 gram per mole. And that gives us an N value of 2. So once we have our N value, how many of these formula units do we have? 2. So then let's write that out. Let's write that out. So if we have C3, H4O4, and we have N is equal to 2. One way that I like to make things a little bit easier if you're more algebra inclined is you take each of your subscripts and you just multiply them by N. So what would I multiply each of these subscripts by? 2. So that in turn would give me C6H8O8. And all we have to do in the end is write out each of our new subscripts in for our molecular formula. So this is the step-by-step guide and procedure to go from mass percent all the way to the molecular formula. And this is what you'll be expected to do on exams. So we did an example together, but what I want you now to do as our last example for today is I'd like you to determine the formula of a compound that is 56.4% phosphorus and 43.6% oxygen, and we know its molar mass is 220. So I want you to figure out the molecular and empirical formula for this compound. Keep in mind, and I would highly recommend that you use, to get the mole ratio, you use our simplified equation if you're comfortable using that equation. So this is the shortcut that we developed to calculate the mole to mole ratio given the mass percent and our atomic masses. And I would recommend using that if you want to save a little bit of time, but you aren't required to. First, the phosphate. Oh, I mean, you can use whatever method was the book. There's no okay. The way that you have it is fine. Yes. Yeah, both are fine. Oh. Yep. Yep. Oh, okay. So first things first, we're going to take 12 times 3.
plus 4 times 1 plus 16 times 4 gives us 4. And just make sure to push the plus sign.
Yeah.
Since probably what happened is the plus sign missed, and then when you hit multiply, it multiplied the image again. Yep. But no worries. Yep, looks good. Everything going okay? And just make sure you're specific on what you designated as 2 and what you designated as 1. Where's the 220 coming from? But yes, exactly. The molar mass is used way later. Everything going okay? Okay, looks good so far. Everything going okay so far? And these molar masses are the masses of your LPs.
Wait, is this molar mass the whole thing or just?
Oh, this is the whole thing.
Oh.
The molar mass in this equation is the mass of your LPs.
Okay.
Yeah. Everything going okay? Oh, so if you have the mass percent of phosphorus in here, and let's get the moles of phosphorus will be divided. So that's the mass of the whole compound. These molar masses, the masses of each of your elements. So you divide by the molar mass of phosphorus from the periodic table. Yep. Everything going okay? Oh, you have this setup. Yep, looks good. Looks good. Oh wait, you have it reversed. The mass of the molar weight 2 is 1. Yep. That's why the ratio seems super large. Everything going okay? Everything going okay? Okay, so that's your ratio. What is N2 representation? Yeah, so this is saying 0.66 moles of phosphorus per mole of water. Okay. First, you need to take the mole ratio and convert it to whole number. This is the decimal. We're going to figure out how to convert it to a whole number using the table. The table of contents. Yeah, it's the top. Yeah, because the way you get moles is by dividing by
Yeah.
looks good. Any questions so far? Oh, you got it. So 2.8 is an 18 Oh, so you get 1 point. Okay. And now your goal is to I'm trying to put some labels. So this is N2 over N1. So what moles are on top? What do you have as N2? Or you can ask for something.
No, I was just worried, but I'm like, last week I Yeah, because you set it up the same way. That's just for the last one. That's just where you go once you get your phosphorus. Once you get the whole number, then you go back and
So I saw a lot of reasonable answers. This is quite good. So let's now talk a little bit about what we are doing here. So we're going to arbitrarily designate N2 and N1. So what do we want our N2 to be? What element do you want to have on top of this ratio? Let's do oxygen. Let's do oxygen. You can do phosphorus. There's nothing wrong with that. Okay, so let's say N2 is oxygen. Okay, so then mass percent 2 is going to be the mass percentage of oxygen, which is 43.6%. And what is the molar mass of oxygen? Just the molar mass of oxygen from the periodic table. 16. Yep, 16 gram per mole. Okay, now because we have already designated oxygen as N2, N1 then of course is going to be phosphorus. So N1 is going to be phosphorus. And what is the mass percentage of phosphorus given in this problem? What is the mass percentage of phosphorus given in this problem? Yep, 56.4. The molar mass of phosphorus is about what? 31. Okay. So now we're ready to plug this in to our equation. So N2 over N1, I always like to label my units. I always like to put labels on my units. So N2 over N1 is representing the moles of what? What did we designate as N2? Oxygen. So this is the mole ratio of the moles of oxygen per mole of phosphorus, okay? And I want you to do this labeling step so that way you don't get confused in the next section. Now we're going to plug in our mass percent. We have 43.6% over our molar mass of 16 gram per mole times, and then now let's switch pen colors. Whoops. Times 31 gram per mole over 56.4%. And that in turn gives us a mole ratio. So N2 over N1, or the moles of oxygen per mole of phosphorus. Let's calculate it. So we have 43.6 divided by 16 times 31 divided by 56.4, and we get a nice, relatively clean decimal. That's your first sign that you've done the calculations correctly. Your decimal does not look too weird. So this gives us 1.5 moles of oxygen per every 1 mole of phosphorus. Perfect. Do not round these numbers off. You have to multiply by a whole number to generate your empirical formula ratio. So then, with this idea established, if we check our table for 1.5, what do we need to multiply 1.5 by in order to get a whole number? 1.5. What fraction does 1.5 correspond to? 3 over 2, or you can think of it as 1 1/2. So then, what do we have to multiply 1/2 by to get rid of the fraction, to get rid of the denominator? 2. So then, we're going to multiply this mole ratio by 2. And since we have moles of phosphorus on the bottom, what are we going to multiply? 2 moles of what? 2 moles of phosphorus. Does that make sense? Okay. So then, that in turn gives us, we have 3 moles of oxygen and 2 moles of phosphorus. So what would our empirical formula be? Yep. So that would give us an empirical formula of P2O3. So this is our empirical formula. Now, to finish off this problem, we're going to calculate N. So to calculate N, we need the molar mass of this empirical fragment, which if we punch it into our calculator, we have 31 times 2 plus 16 times 3. We have a molar mass of 110 gram per mole. If we compare it to our overall molecular weight, the actual molecular weight given in the problem, reading off from the problem, what molecular weight are we given for this compound? What molar mass are we given? 220. So then, let's plug that in now. So our actual molar mass is 220 gram per mole. N is equal to 220 over 110, which gives us an N value of 2. So then, instead of P2O3, what do I need to multiply each of these subscripts by? By 2. And that in turn gives us P4O6. So that is an example of a start to finish calculation of your molar mass and molecular formula given the mass percentages. What you'll do next time is you'll calculate multiple empirical and molecular formulas using this exact same method. So that's all we have for today, and we'll do multiple examples next class session.